Yes, so the equations are derived from the conservation of momentum and mass. And since we consider incompressible fluid, meaning that the density of the fluid remains constant, so mass conservation is nothing but the divergence precondition. And in the first equation, the rate of change of momentum of fluid particle will balance with force generated by difference in pressure and friction. So here, positive parameter nu is called viscosity, and it measures how sticky the fluid is. So for example, water will have smaller viscosity than honey. So in the study of fluid dynamics, one of the great mysteries is the turbulence, and that is even for physicists. So to better understand these turbulent flows, we are particularly interested in small viscosity flows because those tend to be turbulent in the same velocity and length scale. And you can even consider even extreme case by setting viscosity equal to 0. An equation with 0 viscosity, which means that there's no friction term, is called the Euler equation. And my talk will be mainly about this equation. Okay, so for these Euler equations, we have one important property, which is called the energy conservation for smooth solutions. Here, what I mean by energy is the total kinetic energy, defined as the half of the square integral velocity on a whole spatial domain. And in this talk, I will fix my spatial domain as torus. And if the solution is smooth, that means that it is differentiable in space-time, so that every term in the equation makes sense. Then we have the total kinetic energy will be conserved in time. In other words, it satisfies the following equation. So this equation can be easily verified. If you inner product the momentum equation with the velocity, then this is gonna be what you're gonna get by simple product rule. And since the velocity is divergence free, the second term can be written as a divergence form. And now if you take the integral on a whole periodic domain, the second term will disappear because of divergence theorem and periodic boundary condition. And what's remaining leads to the first equation. And if you do the similar computation for smooth Navier-Stokes flows, you're gonna get the following equation. And obviously, the right-hand side term comes from the friction terms. And in general, it is positive. So it says that in the case of Navier-Stokes equation, we have the kinetic energy, the total kinetic energy will dissipate because of friction. And of course, you will recover the conservation equation when you plug viscosity 0. On the other hand, according to Kolmogorov-Zero's law, for turbulent flows, we have the anomalous dissipation, which means that in a vanishing viscous limit, the mean energy dissipation rate doesn't converge to 0, rather it converges to some strict positive number. So it means that even though you send viscosity to 0, there is still remaining dissipation. What's the source of such dissipation? Sorry. Yeah, so for this phenomena, Onsager answered that such dissipation can originate from the smoothness, a lack of smoothness of solution. And he even proposed the threshold of the smoothness of solution for the conservation. So, which is called the Onsager Conjecture, as already introduced in the previous talk. So to quantify to quantify the smoothness of the solution, he considered the alpha Holder continuity, meaning that it satisfies the following inequality. And one can simply consider it as a fractional number of differentiability. So if an Euler flow is alpha Holder continuous for alpha greater than 1/3, we always have energy conservation, while alpha is less than 1/3, then the conservation may fail. And to be slightly more rigorous, one may ask if solution is no longer differentiable, in what sense does it satisfy the equation? Well, for this, we need to introduce more general notion of, is everything okay?
Do you have your computer turned up? Can you mute the volume coming out there? I don't know, because I hear this noise, but
yeah, I also
seem to be an issue. Zoom, but I don't know where it would come from.
I turned
You're
off
muted.
the volume, but I still.
Everyone's muted, but you are the one, so I don't know where that's coming from.
Okay. Let me continue. Yes. Yes. So for that, we need to introduce a weak solution, and for weak solution, so in this general notion of solution, we can even define solution for the square integrable function in space-time, and they satisfy the equation in distribution sense. Okay, so this conjecture is no longer conjecture, and it is completely resolved several years ago. And there are many contributors, but this is already mentioned in the previous talk, so let me omit it. And so now, once you have the Onsager theorem on hand, then we have, in particular from the non-conservative part, we constructed the non-conservative weak solutions. Then the natural follow-up question would be, are the constructed solutions physically acceptable? Physically acceptable Euler flows are expected to be vanishing viscous limit of physically acceptable Navier-Stokes flows. And among all knowns, most physically reasonable Navier-Stokes flows are suitable weak solutions. So in that sense, this question can be reduced to the following: whether the constructed solution can be recovered as vanishing viscous limit of suitable weak solutions to the Navier-Stokes equation in some topology. But this question is very challenging. So instead, what one can do is one can consider weaker notion of solution than suitable weak solution, for example, just weak solution. Then we get the positive answer, and which was done by Buckmaster and Deco. On the other hand, one can derive the admissible condition assuming the vanishing viscous limit. So in this direction, Duchon and Robert proved the following: if an Euler flow can be recovered as a vanishing viscous limit of suitable weak solution to the Navier-Stokes equation in L3 topology, then it should satisfy the local energy inequality. So this means that one can use the local energy inequality as a ruling out condition for the physically irrelevant solution. And the local energy inequality as it is has some physical meaning. Indeed, the equality always holds for smooth solutions. And in that case, in every local region, in a spatial domain, the rate of change of kinetic energy will balance with the energy flux through the boundary. And then this inequality implies that there will be an extra, we allow the extra kinetic energy dissipation in every local region, but we prevent any creation of extra kinetic energy. So with this local energy inequality on hand, one can consider a strong Onsager conjecture, which combines the Onsager conjecture with the local energy inequality. So more precise statement for the conjecture is as follows: for any alpha less than 1/3, there are we can find alpha holder continuous weak solutions to to the Euler equation, which not only have total kinetic energy dissipation, but also satisfies the local energy inequality. So for this conjecture, we have few known results. The bounded solutions are constructed by Duralist and cyclicity, and alpha whole continuous solutions are first constructed by Hisseth up to the threshold of 1/15, and the threshold was recently improved by 1/7, up to 1/7 by Camillo and myself. And for this, the whole continuous solution actually satisfy local energy inequality strictly. So it has a extra kinetic energy dissipation in every local region. I have few minutes left, and for the remaining time, let me move to the compressible Euler equations. So Sam already talked about this. So you can consider this is a generalized version of the Berger's equation. So for compressible fluid, you can simply imagine water, imagine air, and in this case, the density varies in space-time. So if you see the equation, the density will be our new unknown functions, and density with the velocity describes the momentum. And the equations are again derived from the conservation of momentum and mass. But the one difference is that the pressure will be no longer unknown, rather it is a function of density. Okay, so for this equation, we know the existence of unique smooth solution for a short time, but in many cases, such smooth solution lose differentiability in finite time. And to talk about such solution after such blow-up time, bounded weak solutions are naturally introduced. But the problem is these solutions are not unique, which means that even though you start from same initial data, you can have two or infinitely many solutions. So to avoid this, the following admissible conditions have been introduced. And as you see, it is analogous to the local energy inequality for the incompressible Euler equation. Then the question would be, does this admissible condition really serve as a selection principle for bounded weak solutions? The answer turns out to be no. This is done by Duralist and cyclicity. But if you see the construction in their work and even all follow-up works, all constructed solution contains the discontinuity. Then one can ask, if we avoid such discontinuity, meaning that if we only consider continuous solution, will the admissible condition be a selection principle? Again, answer turns out to be no, and this is my recent work with Vikram Giri. I think time's up, so let me stop here.
Which dimension is this?
3-dimensional.
Question, do you believe in the existence of smooth solutions for the Euler equation?
Existence of smooth solution
It's a smooth
For all
initial
time.
data, yeah. Mhm.
for all time. Can I just say my belief?
Yes, that is, I asked for your
I couldn't explain the reason. It's
Yeah.
like, yeah, but I don't know. I guess it'd be no, but it's because so far we haven't had any, good way to make it work.
Okay, no, I'm asking that question now for many years. So when I was at Courant, of course, there were a lot of people around.
Mhm.
And what was interesting, so Andy Maida at some point said the same like you, and then later he switched sides.
Oh.
And he was talking about a miraculous cancellation.
So he become more,
So,
he moved to positive side. Yeah, maybe he saw the cancellation in his,
revelation or cancellation.
yeah.
Okay, thank you very much.